the exponential function y equals e to the power of x. Now this function is special for a whole number of reasons, but I'm going to talk about what makes this function so special from the point of view of calculus. Now firstly, the base e is an irrational number that's approximately equal to 2.71828. Here's the number e on a calculator. So we get to that by pressing the shift key, then pressing ln, then pressing the number 1, pressing equals after that, and that's the value e, correct to 9 decimal places. The gradient of the tangent to the curve y equals e to the power of x at the y-intercept 0, 1 is 1. So that is f dash of 0 equals 1. So here's a sketch of y equals e to the power of x. It's not the scale, of course. The red line represents the tangent to the curve at the y-intercept. So what this is saying is that the gradient of the tangent at the y-intercept is equal to 1. The function y equals e to the power of x is special because dy dx is equal to e to the power of x. So in other words, if I differentiate, or we differentiate e to the power of x, the result is e to the power of x. So the derivative is equal to the function. And it is the only non-zero function where dy dx equals y for all real x, not for just any particular value or one or two values of x. There are other functions where if you differentiate the function at particular points, the value of the derivative at that point is equal to the value of the function at that point. But the function y equals e to the power of x, wherever it's differentiated, the value of that derivative is equal to the value of the function at that point for all real x. Now looking at the derivative by first principles, so the derivative of e to the power of x by first principles using the limit definition, so f dash of x is equal to the limit as h approaches 0 of e to the power of x plus h minus e to the power of x over h, and just focusing at a particular point, so at the point where x equals 0, so f dash of 0 equals the limit as h approaches 0 of e to the power of h minus e to the power of 0 over h. We know that equals 1 because f dash of 0 equals 1. So by rearranging this limit and eliminating h, we can come up with an expression that approximates the number e. So if we just quickly go through that together. So first of all, f dash of 0 is equal to the limit as h approaches 0, e to the power of h minus e to the power of 0 over h, and the value of that limit equals 1. Now because this limit equals 1, we can flip the fraction. So the limit as h approaches 0 of h over e to the power of h minus 1 is equal to 1. Now I'm going to break up this fraction. So the limit as h approaches 0 of 1 over e to the power of h minus 1 multiplied by h is equal to 1. Now if we let 1 on n equal e to the power of h minus 1, then h equals the log to base e, or log of base e, of 1 plus 1 on n. Okay, so what we're doing is that we're going to eliminate the h and replace it with n, or substitute out the h and substitute in its place an equivalent expression in terms of n. Now also the h changes as well. So as h approaches 0, n approaches infinity. So in other words, the h is replaced then with the n, and instead of h approaching 0, it's replaced with n approaches infinity. Now if we substitute for 1 on e to the h minus 1 times h, but the equivalent expression in n, we have n times the log of base e of 1 plus 1 on n, and that's still equal to 1. So applying a log law now, so this n comes out sort of to the back there, so it becomes a power. So moving on, the limit as n approaches infinity of the log of base e of 1 plus 1 on n, all to the power of n, is equal to 1. And taking raising this to base e, so that cancels out the log, we have lim n approaches infinity, 1 plus 1 on n to the power of n equals e. So just imagine that we can raise both sides of this equation to base e, so the e and the log of base e will cancel, and then you end up with e to the power of 1 on this side. So what you end up with, then apply the limit. So in other words, 1 plus 1 on n to the power of n as n approaches infinity is then equal to this number e. So I'll just move the board up there. So if you want to test this, for example, and substituting n equals a million, you'll end up with a value that's very close to e. And the bigger the value of n, the closer the value of e that we get to.